There are two remaining categories of indeterminate forms that we haven't encountered yet, at least not in the context of L'Hopital's rule. One is infinity minus infinity. This one's indeterminate because you can't tell which infinity wins. One is trying to make the whole thing big, and one is trying to make the whole thing small, and you can't tell which one wins. So that's indeterminate. The other indeterminate form are actually three different indeterminate forms that all involve exponentials. So 0 to the 0, infinity to the 0, and 1 to the infinity. And these are all indeterminate because you can't tell which one wins, the base or the exponent. In the case of 0 to the 0, the base, since the base is going to 0, that wants to make this whole thing 0. But since the exponent is going to 0, that wants to make this whole thing 1. So you can't tell which one wins. Is it going to end up close to 0 or close to 1? Or maybe somewhere in between. We can't tell. So this is indeterminate. For infinity to the 0, the base is trying to make this big because it's infinity. The exponent is trying to make this close to 1 because the exponent is 0, and you can't tell which one wins. And then finally, for 1 to the infinity, when the base is 1, right, if the base wins, then we'd have 1 to some power, and that would be 1. But if the exponent wins, then we should be blowing up to infinity, and you can't tell which one wins. So these three things are all indeterminate. It's a little hard to remember that these are indeterminate because, right, 0 over 0 is clearly indeterminate because we're so used to the fact that dividing by 0 is problematic. Infinity over infinity is kind of clear it's indeterminate because there are infinities around. So maybe it's clear that infinity to the 0 is indeterminate. But 0 to the 0 and 1 to the infinity tend to surprise people. So when there are exponentials around with zeros and or infinities, be careful. So let's look at an example of each one of these types, or at least one with the difference and one with an exponential. For an example of infinity minus infinity, let's look at the limit as x goes to 0 from the right of cotangent x minus 1 over x. This is an infinity minus infinity type of limit because as x goes to 0 from the right, cotangent goes to infinity, and 1 over x also goes to infinity. So we're getting infinity minus infinity. So what should we do? Well, as with the 0 times infinity indeterminate form, what we should probably do is just try to do some algebra to turn the indeterminate form that we have into one of these two nice indeterminate forms. So what kind of algebra could we do? Well, there are a couple things you might try. One thing you might try is just putting these over a common denominator. But if you do that, that doesn't really help because you end up with x cotangent x minus 1 over x. And then it's hard to know even if this is an indeterminate form because this x cotangent x is itself indeterminate. That's going to give you 0 times infinity. So it's very unclear what happens in this situation. Another thing you might try is, since we have a cotangent floating around, you might just try rewriting everything in terms of sine and cosine. That gives us cosine x over sine x minus 1 over x. Okay, but then what should we do with this? Well, maybe now that we have it written this way, maybe now we should put it over a common denominator. It takes a little playing around to come up with this idea, so I wouldn't blame you if you didn't immediately have this idea, but after playing around with it for a while, you'd probably try this at least. So putting these over a common denominator, we get x cosine x minus sine x over sine x times x. So I'll write it this way. Now this, if we try to evaluate it directly, the numerator is going to give us 0, the denominator is going to give us 0. So this gives us a 0 over 0 indeterminate form. So we can use L'Hopital's rule now. All right, we get limit as x goes to 0 from the right. Now derivative of the numerator, we have to be careful because of this product right here. So derivative of x cosine x is cosine x plus x times the derivative of cosine x, which is minus sine x, and then minus the derivative of this piece, the sine. So that's cosine all over. And then in the denominator, we need to use the product rule again. So we get sine x plus x cosine x. Okay, now this simplifies, right? These are gone. And we're left with minus x sine x over sine x plus x cosine x. And x is going to 0. Well, this actually still gives us an indeterminate form. It still gives us 0 over 0. But we can try L'Hopital's rule again. There's no guarantee that this will actually help, but at least we can try it. So limit as x goes to 0 from the right. Derivative of x sine x is, so that minus sign out front. Now we need the derivative of x sine x, and that's sine x plus x cosine x. Okay, now in our denominator, derivative of sine x is cosine x plus, and now we need the derivative of x cosine x, which is cosine x minus x sine x. Okay. Now what happens when we try to just plug in 0? Well, in the numerator, we're going to get, let's see, 0 from the sine part, and then this cosine is multiplied by x. So x cosine x when x goes to 0, that's 0. So in the numerator, we just get 0. And in the denominator, let's see, cosine x is, as x goes to 0, that's 1. Cosine of 0 is 1. Here's another one coming from that cosine. And then this last piece gives us 0. So we get 0 over 2, but that's 0. So this limit, turns out it's 0, which I think is extremely not obvious. I wouldn't know even what to guess for this limit, but it turns out it's 0. For an indeterminate form involving an exponential, let's look at this one. How about the limit as x goes to 0 from the right of tangent of 2x to the power x? Now if we just try to plug in 0, we get tangent of 0 to the 0, but tangent of 0 is 0, so we get 0 to the 0. And even though there aren't any infinities around, this is indeterminate because when the base is small, this is trying to be 0, but when the exponent is small, this is trying to be 1, and so we can't tell which one wins. So it's a 0 to the 0 indeterminate form, but that is not an indeterminate form that we can use L'Hopital's rule with. To use L'Hopital's rule, we have to have 0 over 0 or infinity to the infinity, or I'm sorry, infinity over infinity. So how could we do that? Well, I mean, as usual with calculus, anytime you have a base in an exponential that is problematic in some way, you can always try rewriting it base e. So what if we write this as limit as x goes to 0 from the right of e to the, so there's going to be an x out here, but this inside piece, tangent 2x, that's e to the natural log tangent 2x. Like this. Okay. Well, now we can do some algebra involving these exponents. So this is limit as x goes to 0 from the right of e to the x natural log tangent 2x. Okay, but exponentiation is continuous. We can evaluate a limit involving exponentiation by just moving the limit to the exponent. Right? That's an okay thing to do because the e to the x function is continuous. So e to the limit as x goes to 0 from the right of x natural log tangent 2x. Okay, so is this an indeterminate form? What exactly is it? Well, x is going to 0 from the right, so this x in front, that's going to 0. And this tangent, 2x, is going to 0 from the right. So tangent, as tangent's input goes to 0 from the right, tangent itself goes to 0 from the right. And natural log of something going to 0 from the right goes to minus infinity. So this gives us a 0 times minus infinity kind of indeterminate form. On the one hand, that's not 0 over 0 or infinity over infinity, so we're going to have to do some further work. But on the other hand, this is an indeterminate form that we've handled before, right? It's a 0 times infinity kind of indeterminate form. So to calculate this limit of x natural log tangent 2x, we just need to rewrite it as a quotient. I'll come back to the exponential. Once we know the value of this limit, we'll just raise e to that power when we're done. Okay, so we sort of already have a plan of action for this kind of indeterminate form, this 0 times infinity indeterminate form. And our plan of action is shuffle one of the things to the denominator. And I'm going to choose the x, so like this, natural log tangent 2x over 1 over x. All right, now this is an infinity over infinity indeterminate form. So now we can use L'Hopital's rule. This is the limit as x goes to 0 from the right of, so derivative of the numerator is going to be a bit of a mess, but that's okay. So 1 over tangent 2x times the derivative of tangent 2x, which is secant squared 2x, times the derivative of 2x, which is 2, all over derivative of 1 over x. Well, 1 over x is x to the minus first, so its derivative is minus x to the minus second. Okay. Now we need to maybe simplify this and see what we get. So 1 over tangent is, right, tangent is sine over cosine, so 1 over tangent is, right, this piece is cosine over sine, and then secant squared is 1 over cosine squared, so we can cancel a cosine, and we're going to get 1 over, let me move this down a little bit. So limit as x goes to 0 from the right, we're going to get 1 over sine 2x times cosine 2x. That's just from these trig pieces. And then there's a times 2. And then also, when we have, so there's a minus sign. Let's get that here. And then this x to the minus second is in the denominator. So that's like having it with a positive exponent in the numerator. Okay. So limit as x goes to 0 from the right of minus 2x squared over sine 2x times cosine 2x. Okay, now at this point we have some options. This is still an indeterminate form. We get 0 over 0, so we could try using L'Hopital's rule again. But we have another option because that denominator, I recognize that from a trig identity. Right? Sine times cosine, that's part of a double angle identity, or half angle identity, depending on which way you look at it. So limit as x goes to 0 from the right of minus 2x squared. Let's see, this is, now I have to remember my trig identities. This is cosine, no, I'm sorry, sine of 4x with a 1/2 in front, right? Because sine of 4x, using the addition formula, that's sine 2x times cosine 2x plus, yes, okay. All right, and for this, so how can we evaluate this? Well, I think, let's simplify. So let's see, we can get rid of this half, make this a 4. And now it is still 0 over 0, but now the derivative, when we use L'Hopital's rule, is going to be much easier. So in the numerator, so limit as x goes to 0 from the right. In the numerator, we're going to get minus 8x. And in the denominator, we're going to get 4 cosine 4x. And then when we take the limit as x goes to 0, that's 0, right? The numerator is going to 0, the denominator is going to 1, so that's 0. So finally, we know the value of this limit that is in the exponent. It's 0, so e to the 0, and so that whole thing is 1. So turns out that the limit as x goes to 0 from the right of tangent 2x to the x is actually just 1.